In our first example today, we want to look at how a calorimetry experiment setup can be combined with what we already learned about heat flow in our previous lecture series to calculate the temperature change that a material will undergo when it's heated. So bear with me for a second because this setup on this problem is a little challenging. And one of the things we're going to look at in this specific example, which is example 9.3 in the OpenStax textbook, is how we have to interpret and kind of parse the information in the word problem so that we can apply it correctly to the framework that we use to figure out the relationship between heat gained or lost and the change in temperature. So here's what we're told. A 360 gram piece of rebar, so rebar is a steel rod that's used to reinforce concrete, is dropped into 425 milliliters of water at 24.0 degrees Celsius. The final temperature of the water was measured as 42.7 degrees Celsius. So what we've seen here is that a piece of steel was heated up. That's the key thing, is that the rebar is steel. So if we want a specific heat for the rebar, we would look at the specific heat of steel. We know the mass of the rebar. It's heated up, but we don't know to what temperature it's heated up, and is then dropped into 425 milliliters of water, which starts at 24 degrees Celsius. So this is the initial temperature of the water. When the rebar loses heat, the water absorbs that heat, and so the heat lost by the rebar must be the heat gained by the water. When the water is done heating, the maximum temperature of the water was measured to be 42.7 degrees Celsius. We want to calculate the initial temperature of the piece of rebar. So we're going to calculate initial temperature for the 360 gram steel sample that we have. We're asked to assume that the specific heat of steel is the same as that for iron, which we can find in table 9.1. And this is key to a word problem like this, or a well-designed calorimetry experiment, is that we're assuming when we measure this temperature of the water, that all the heat transfer occurs between the rebar and the water. So the calorimeter in which we're running this experiment doesn't lose any heat right away to the surrounding environment. So in terms of our problem-solving strategy, first we want to get down a couple of numbers. The big idea in our problem-solving strategy is that, as is ever the case, the negative heat lost by the system is equal to the heat gained by the surroundings. So negative Q sys equals Q surroundings. Heat lost by the system equals heat gained by the surroundings. That's key in any calorimetry experiment. So what we want to do ultimately is define all the parameters that would represent the heat lost by the steel and the heat gained by the surroundings. So if we look at table 9.1, the specific heat for steel is 0.449 joules per gram degree Celsius. We know that the mass of the steel is 360.0 grams. We know that the final temperature of the steel, and this is another thing that you have to interpret from the problem, because the steel will cool down to the point where it's the same temperature that the water can hold, the final temperature of the steel, when the temperature of the water maxes out, must be the same as the final temperature of the water. They have to be in thermal equilibrium with each other. So this is going to be an important point. Not only is 42.7 degrees Celsius the final temperature of the water in this calorimetry experiment, but as long as we assume that the calorimeter isn't losing heat to the surroundings, which is a valid and important assumption, the final temperature of the steel must equal the final temperature of the water in this case. So we can say that the final temperature of the steel is 42.7 degrees Celsius. So the way we solve the problem is if we say that the heat lost by the system is equal to the heat gained by the surroundings. We want to define the same set of parameters for water that we did for the steel, and we're going to say, okay, if we can find the heat gained by the water, the Q surroundings, then we can figure out the heat lost by the steel, and we can use that to calculate the initial temperature of the steel. So the mass of the water we can find by using the density of water. If we have 425 milliliters of water at room temperature and anywhere up to about 50 degrees, so it's valid for this problem, the density of water is 1 gram per milliliter. So 425 milliliters of pure water would have a mass of 425 grams of water, anywhere near room temperature. We know that the specific heat of water is 4.18 joules per gram degree Celsius to 3 sig figs. That's again in table 9.1. And the temperature change for the water is equal to 42.7 degrees Celsius minus 24.0 degrees Celsius, final temperature minus initial temperature, giving us a temperature change of 18.7 degrees Celsius for the water. All right, so now we get to the main crux of the problem because we've got all our parameters down, we've got all our constants down. We come back to this idea that the heat lost by the steel is equal to the heat gained by the water. So we can use the calorimetry formula to say that the negative mass times specific heat times temperature change of the steel is equal to the positive mass times specific heat times temperature change of the water. We know the mass, the specific heat, and the temperature change for the water, and we know the mass and the specific heat for the steel, so we can solve this equation for the temperature change in the steel, delta T, and we're going to use that to find the initial temperature of the steel. The way that looks is we plug in the mass of the steel and the specific heat of the steel over here, 360 grams times 0.449 joules per gram degree Celsius. We're going to let the temperature change delta T be x on this side of the equation is equal to 425 grams times the specific heat of water, 4.18 joules per gram degree Celsius, times the temperature change of the water, 18.7 degrees Celsius. The heat lost by the steel is equal to the heat gained by the water. So we have the parameters for steel on the left-hand side, the parameters for water on the right-hand side. If we evaluate the right-hand side, 425 times 4.18 times 18.7, we get that the water has gained 33,220.55 joules. So the left-hand side of our equation must be equal to negative 33,220.55 joules because all the heat gained by the water came from the steel. So a negative sign got cut off here in the transfer to the PowerPoint slide, but this should be negative 161.64 times the temperature change in the steel is equal to 33,220.55 joules. Delta T steel, cross this out on your sheet and make sure this does say delta T H2O. This is my mistake. Delta T steel is equal to 33220.55 joules divided by negative 161.64 joules per degree Celsius. The joules and the joules cancel. We find that the temperature change for the steel is negative 205.5 degrees Celsius. So our steel bar, our piece of rebar, lost 205.5 degrees Celsius in its temperature. Therefore, and we know from the problem setup that the final temperature of the steel has to be the final temperature of the water. So the final temperature of the steel is 42.7 degrees Celsius. We can say that the final temperature of the steel must be equal to the temperature change minus, we can write an expression for the temperature change of the steel. Delta T, steel, is equal to the final temperature of the steel minus the initial temperature of the steel. Our delta T steel is negative 205.5 degrees Celsius. Our final temperature for the steel is positive 42.7 degrees Celsius. Our initial temperature of the steel is minus x. If we rearrange and evaluate this equation, we move the x over to the left-hand side by adding x to both sides. We then move the 205.5 degrees Celsius over to this side of the equation by adding 205.5 degrees Celsius to each side. And we get that the initial temperature of the steel was 205.5 degrees Celsius plus 42.7 degrees Celsius. The initial temperature of the steel was 248.2 degrees Celsius. So the initial temperature of the steel would report to 3 sig figs because all of our measurements have at least 3 significant figures. The initial temperature of the steel is 248 degrees Celsius. All right, so be aware, once you get into the math, the steps in the math are pretty straightforward. The hard part about calorimetry problems is correctly setting up the picture of what's happening in your head and making the connection between conceptually what has to be going on and where the variables line up in the equation. So I would say you're always going to be able to handle the math and the mathematical operations associated with solving these problems. So when you sit down to solve the calorimetry experiment, take some time, run your ideas past your friends in some form or fashion, and discuss how you're setting up the system, how you're defining the surroundings, what the mass and the specific heat is for the system versus the mass and the specific heat for the surroundings, and make sure you understand where you're getting your information for the final and initial temperatures in the word problem. The hard part in a calorimetry problem is always defining system and surroundings in a useful way so that you can see how the math relates to the conceptual picture that we're trying to put together. If you're having trouble with that, that's an excellent thing to ask me about during office hours or anytime you can get a hold of me. It's a natural thing to struggle with, but if you kind of avoid it and run away from it, it's not really going to get better. If you get in there and you run up against it and you engage with it a little bit, it'll be frustrating in the short term, but it will yield to you and you'll get the skill and be able to define system versus surrounding in a reproducible way. These problems will become a lot easier. We're going to practice this again. We're going to come back for another calorimetry example in a few minutes, and I'll see you there.